Thank you, everybody, so much for coming. I know it was a long day, lots of sessions, lots of great sessions, but it is a long day, and you came all the way across the campus for this talk. Thank you so much. And I'd also like to thank the organizing committee. It's been a fantastic conference so far, as I think everybody will agree. Great food as well, great talks with everybody. It's been a great event so far. And this beautiful venue, I couldn't ask for more. Thank you so much. So this is kind of quite a challenging talk. I was thinking about it last night, like probably too late at night, thinking, okay, so over the next 45 minutes, I'm going to kind of take you on this journey into AI and kind of explain what these models are doing and how they relate to what we're going to be doing. So it's a little bit difficult, but so hopefully it will go okay. But yeah, what I'm going to try and do is first explain what this title means, like what are these stochastic parrots. I'm going to try and explain how they work, and then why they might be interesting for us corpus linguists, okay? And then at the end of all of that, hopefully by that point you'll think, oh, okay, I know what these are, and they're useful for us, and they're interesting, and we should know more. And then at the end, I'm going to introduce a new platform, which is part of Bangkok, of course, which will help you kind of facilitate that kind of bridge and that new maybe step into AI. And allow you to very easily play and try out these ideas. Of course, though, I know from the talks I've been attending these last few days, there's some very great experts in this area. And in 45 minutes, I cannot really give this topic the justice it probably deserves, so please forgive me when I simplify things a little bit. And maybe in the Q&A, you can challenge those explanations and say, no, it's actually more like this, and that would be great too. Okay, so let's start with stochastic parrots. Okay, so if we think of AI, probably the first thing, well, certainly back in the day, people would be thinking of this AI. HAL 9000 from the 2001 Space Odyssey movie, and the book before that. But we had this case where one of the, it's a spoiler. But one of the guys is kind of outside the spacecraft, and it's like, there's this HAL trying to control everything, and the other guy says, please open the bay doors. And he says, I'm sorry, Dave, I'm afraid I can't do that. And I won't let you know what happens to the guy outside after that. But kind of AI's had that kind of reputation of being a bit scary, not sure if we can control it. And of course, the story was said in 2001, and now it's 2025, and we have this. It's kind of similar, actually. OpenAI ChatGPT has been around for a few years. And is it like HAL? Well, let's just try it out and see. Okay, so this is ChatGPT. And let's hope the internet's working. Hello.
Hello. Everything seems to be working fine on my end.
Okay, great. Okay, just wait. Just a minute. So we're here in Birmingham learning about the possible impact of AI on corpus linguistics, okay? So can you just say hello to everybody and introduce yourself?
Hello, everyone in Birmingham. I'm ChatGPT, an AI here to help with your questions and discussions. It's great to be part of your session on the impact of AI on corpus linguistics.
Okay, yeah, thanks. Okay, great. So we are doing corpus linguistics. So how would you define corpus linguistics?
Corpus linguistics is the study of language as expressed in corpora, which are large and structured sets of texts. It involves analyzing these texts to understand language patterns.
Actually, okay, it's okay. We know, we're actually pretty good at that. Okay, that's great. But we had a really great session just today on keywords and these continuous keywords and so on. It was really interesting. So if I had a target corpus of, say, bioscience research articles, and I wanted to compare that with a reference corpus of general English, right? What keywords would I get from that?
Keywords are words that appear significantly more frequently in one corpus compared to another.
Yeah? Yeah, I said, wait. What would the keywords be for a corpus of bioscience?
In a bioscience corpus, keywords often include specialized terms related to biology, medicine, and related scientific fields. For example, you might find keywords like genome, protein, enzyme, mitochondria, or CRISPR.
Okay.
These terms.
Okay, that's great. Thank you very much, ChatGPT. I'm going to say goodbye to you now.
You're welcome. Have a great time with your session in Birmingham.
I will. Thank you. Okay. So it kind of feels a bit different to Hal. It's kind of like really, like trying to be really friendly and helpful. Some people hear that and think, wow, that's like really human. Like, is she actually understanding what we're saying and responding? And like, is there sentience there? Is she conscious of what's happening? But there's other people that would argue, no, it's actually not that at all. It's actually just a simulation, mimicking. It's like a parrot. When you say, hello, hello, and it says, hello, it's like, responds like in English, and you start thinking, oh, that parrot understands me. Well, when it says, Polly want a cracker, which is apparently a famous line from an old advertisement, you hear that and you don't actually think these parrots understand you. They're just mimicking and copying what you've done before, right? So this is the debate to some degree within AI right now. It's what is actually happening when what we just experienced. What is that? So the stochastic parrot is actually a really topical word right now. And in the American Dialect Society, it was the AI word of the year in 2023. Stochastic parrot, I'll explain what it is. So LLMs, or these large language models, like kind of you just heard one of them go, are these stochastic, meaning probabilistic models. They generate outputs by predicting the most probable next word or token based on the training data. So it's just probabilistic next word. And if you go further from that, well, they're just probabilistic models, which means they lack a true understanding of the language, like that parrot. Like a parrot in your house. So they generate text that may seem meaningful, but they don't have intentionality, beliefs, or, and this is a focus of today's talk, an understanding of the language. That's the idea of a stochastic parrot. And this discussion was really hit off recently. This is Emily Bender and her team's discussion. This is 2021. So it's all very new. ChatGPT's only been around for years or so. So in this paper, they were discussing the dangers of these stochastic parrots. And they were saying that these are not performing natural language understanding and only have success in tasks that can be approached by manipulating linguistic form. And furthermore, the tendency of human interlocutors to impute meaning where there is none can mislead both the NLP researchers and the general public into taking synthetic text, this parrot text that we just heard, as meaningful. So it's basically saying, in some sense, what we just heard is not meaningful at all. Okay. Now, what's really fascinating about this discussion is that in the world of AI, even top-level people in AI are also questioning what we're actually experiencing in this world of ChatGPT and other language models. So Chris Manning, great guy if you ever get to meet him, really, really lovely person. And he is professor of linguistics and of computer science at Stanford. He's one of the leading AI people, and he said this: LLMs and other generative AI are enormously powerful because they soak up, abstract, and mash up the work of millions of humans, but they are only a bit more intelligent than an encyclopedia. Just a little bit more. It's kind of interesting. Central to intelligence, which they don't have, is the ability to learn, adapt, and act in novel situations. So the claim is that what you just heard can't do that. Okay. Another really leading person in AI, Yann LeCun, who is the chief AI scientist at Meta, who's building these models, says this: LLMs are good at manipulating language, but not at thinking. I think the shelf life of current AI paradigms is fairly short, probably 3 to 5 years. He said that this year. So in 5 years' time, he's predicting these models are dead. And we'll have a different paradigm where they actually understand. Okay. Okay, and there was an interesting part about the parrot, because there was a story on the internet about this parrot being able to call its friend by tapping on a cell phone. And when he heard about that on Twitter, he said, looks like calling LLMs stochastic parrots might constitute an insult to parrots. That's how stupid they are. Okay, now that's the negative side, but there is another side to this, and I'm actually on this side. I'll put that right out at the beginning. And I'm going to try and hopefully explain why I'm more on this guy's side as we go through the next few minutes. Ilya Sutskever was the chief scientist at OpenAI. He left and started his own company on ethical AI. But he said this: I think the most beautiful thing about deep learning, what we experience, is that it actually works. Because you've got these ideas, you've got this little neural network, you've got this back propagation algorithm. So maybe if you make it large, if you train it on a lot of data, then it will do the same thing that a brain does. That's the idea, and it turns out to be true. And he's convinced these are like our brains. And he's got some kind of evidence for that, because if you actually, what we just experienced a few minutes ago, I'm getting useful information back from these systems. We can use these systems for information retrieval, text generation, translation. We can use them as chatbots. We can generate code with them. And you've probably seen, maybe some of you have seen these examples before, but what is the most famous place in Japan? And ChatGPT says the most famous place in Japan is often considered to be Mount Fuji, and goes on. Okay? Write one sentence definition of corpus linguistics. There you go. We actually heard the EA saying that. Okay, and like translate it into Japanese? Sure. Corpus gengo gaku to wa daikibou no jisai no gengo de corpus o moji te keisan teki no oyobi toke. I'm showing off, so. Can you help me? Of course. What do you need help with? Yeah? And then write a Python script to generate a word list from a folder of text files. That's like a word list from Hancock. Sure, there you go. They're kind of pretty smart for a parrot. Okay, but there are problems too with these. It's not all great, and it kind of leads back to why we think they might be parrot-like. They hallucinate. They produce an output that's false or doesn't match our intentions, and they have biases. But there's also just implementation problems like consent and deployment maintenance, scaling, security, and things like that. And I love the examples that I'm going to show you in a second about hallucinations. If you ask a model that hasn't got if you ask the latest models questions, they hallucinate less and less every day. They're getting better. But you ask a smaller, less performant model questions, it starts hallucinating like crazy. So I asked, who developed the Hancock software tool? Thank you, Andrew, for introducing me with that. Well, Hancock is a tool developed by Future Growth Software. It's developed by Digin. It's developed by Ann Taylor. Are you here? It's developed by David Robinson. And the last two is always my favorite. It blew my mind when I saw it. Hancock is a corpus analysis tool developed by Mark Davis. And even worse, and Mike Scott unfortunately had to go early today, but Hancock is a tool for corpus linguists developed by the University of Liverpool, where Mike Scott went. It was created by a team of linguists at Liverpool, led by Professor John Sinclair. Kind of all over the place, right? So, and Ilya Sutskever, who still thinks it's like the brain, admits reliability is currently the single biggest obstacle for these neural networks to be useful, like truly useful. And he said that in 2023. So he's pretty aware of the issues, but they are getting better all the time. Okay, so the first, remember this is stochastic parrots meet corpus linguists. So in this dialogue between them, I thought, okay, here's the first hot take. Okay, large language models appear to have learned the patterns of language. Like, nobody would disagree with that. And then I wrote it and I thought, actually, no, will people agree with that? They've learned the patterns of language? And I thought, oh, maybe that is a bit too controversial, so I changed the wording. Okay, they learned or maybe acquired or maybe mimicked, maybe captured the patterns of language. And they mimic it. But then I attended Gavin Brooks' talk on Monday. I thought, oh, no. Okay, in certain contexts. And then we had Lizzie's talk on the next day about conversation with all the complexity of that. Okay, so in limited context, maybe, they certainly have captured the patterns of language in some way. Whether they're intelligent or not, they're certainly capturing the patterns to some degree. Okay, so as corpus linguists, should we be interested in what patterns they have learned? And I think the answer to that is pretty much yes. Even if they don't match our patterns, it's like, what patterns have they got? And I'm happy to see that even in this conference, we had a lot of people looking at the patterns that AI generates and comparing it with humans and seeing where the differences are, because maybe that would lead to better models or better understanding of language. And the next question, though, which is perhaps less looked at, is, as corpus linguists, should we be interested in how the patterns were learned by the AI? So how do these work? I don't see as much of that, but I think that's almost maybe more interesting in some respects. So we actually start the talk right now. That was the opening. Okay. So I'm going to try and answer 3 questions. What are large language models? We've seen it in action, but what actually is it? What can they tell us about language, if anything? And how can we advance corpus linguistics and also LLM research with that understanding? Okay. So let's start with the first question. What are large language models? This is going to get difficult now, a little bit. Okay, I tried my best. Bear with me. So large language models are usually transformer-based neural networks designed to represent, process, and often generate natural language. They are part of a broader family of AI models, including generative AI and discriminative AI. Okay? And if we think about neural networks, we think of this. This is a human brain neuron. And it's trying to simulate what's happening in the brain to some degree, but we can't do that with an algorithm, so we have something much more simple. If you come back here, you have the dendrites, and they come into the nucleus and send off some signal along the axion. And we have the same. We have these signals coming in with these weights, and then we have a bias and a function that sends out a signal. So we kind of do that, and then we kind of put them together into a network. And the old networks were really small because the computers weren't very powerful, but when we have a big network, maybe it will act like a human, and that's what Ilya Sutskever was saying. When we make it big, then it starts acting like a human brain. So you can imagine, like, we send in an input like I, and this is a sentiment analysis tool, say. And in there, something magical happens, and the output is I is a positive. You have a positive feeling about yourself, maybe. But then you have the word love, and of course that goes through this magic box, and it comes out, that's positive too. And then the next word comes in AI, and in the magic box it realized that, well, maybe the sentiment about AI is negative. That's the kind of idea of these neural networks. Okay. And as this gets more complicated, it actually is able to represent more inputs and outputs and decisions and so on. Okay. So that's the kind of basic idea of these, with input, output, and then the black box in the middle in some way. And in 2017, so recent, only 8 years ago, some team at Google came out with this idea of attention is all you need. And it's a kind of model, it's making that model, but much more complicated, more inputs, outputs, and more black box in the middle. And that suddenly was able to act really good. Started performing really good. At translation, this is a translation model, suddenly outperformed every other rule-based translation model I've ever seen. And if you're around in Birmingham next week, Jack Greaves, where is he? Is going to be giving the Sinclair lecture called Corpus Linguistics is All You Need, and it's echoing the idea of that. So attention is all you need is this amazing model, but actually it's old now. 8 years, it's all old now. The modern architecture is this transformer model like this, single block. It's called a decoder model. And Sebastian Raska, who I met in America last year, was very cool as well, wrote a great book on this, building a large language model from scratch. And this is what it looks like. Now, this is complicated. I'm just going to whiz through, and then I'll go through some of the components. But it starts out with a sentence. Every effort moves you. What's the next word? That's what it's trying to do. Okay, so it projects these words, it tokenizes it, projects it into an embedding layer, which we've heard about sometimes in the conference, and then it goes through this really important attention block, and then it goes through a standard neural network, a Phi4 neural network, which I just showed you an example of, just like, and anyway. And then it goes to the final output layer to make the decision. And the next word would be, every effort moves you closer. So that's what it's trying to do. It tries to predict that next word, and then it will send that word back to the beginning and do the next word, and then the next word. So what we have here is the basic design is like this. We've got basically 6 components, But you already know 3 of them, because I introduced them just a few minutes ago. We have the tokenizer that splits the sentence into tokens or words. We also have this feed-forward network, that little magic box that makes decisions. Well, models complex features of the word level to predict the next word. And then the output layer produces the prediction. So we have those 3 components. But the key to a good model is attention is all you need, and it's this part, the embedding model and the attention mechanism. And to get a grasp of what that is, I've got this little graph, and what we have is that we have these words, and we project them into a space, a multidimensional space, and then we learn how these are related to each other. The attention looks at context and says, oh, these words are kind of related, and moves them closer together in the space. Context dependent. So if you had I went to the zoo and I saw this zookeeper feeding an elephant, what's the next word? It would know, oh, elephant zoo and stuff, and it would say, oh yeah, elephant and banana, that's coming closer. And it would more likely say that the banana is the next word from that. But then I went to a jungle and I saw, oh, jungle, oh, that's down there, and then the elephant and the jungle would be moving together. And as these co-occurrences get stronger, we know what's likely to be the next word. Doesn't that sound familiar to Corpus Linguistics? I hope it does. Okay, so that's what a large language model is, in the very simple sense. I know some people here are going to go, what? But anyway, so what can they tell us about language, if anything? So I've got one more kind of complex problem, because the language model isn't just that algorithm. It's actually 3 stages to get to an actual machine that works. So the first stage is to build the language model. And that's what I just showed you. Build the algorithm. It's just code. Just build this framework. Build all these nodes in code and have this mechanism in code. And that's okay. Okay. So when we build this algorithm, there's a few assumptions. So LLMs operate solely on tokens. That's a very important thing to realize. Now, tokens are kind of like words, but they're actually word fragments. So they use a non-standard lexicon, like mischievous would be split up into these 3 parts. And efforts are being made right now to even split those into a character level. So we're not interested in words at all. What is a word? They go let's look at each character and see how that affects every other character and predict the next character. That's the direction. There's no explicit word classes. There's no grammar rules. Things like subjects, verbs, objects, past tense, present continuous, none of that. It's just these fragment tokens. They have no explicit word level or subtext level or text level annotation. That was for Robbie there, who's talked about this before. None of that. No explicit register. Sorry, my friends from NAU. No register. Oh, my background with John Swales talks about genre analysis. There's no genre distinctions, nothing. It's just words. Predict the next word. Which is kind of interesting, right? They can do all that, even though they have none of this in that initial model. And this is really bizarre, actually. So if you go to the tokenizer, you can type in a sentence or something and see how it's represented in the model. And I'll blow it up here. So if you have the cat sat on the mat, the dangerous dog chased after the mischievous cat, that's what the model will see. And you can see mischievous is in 3 parts. Okay, and if you have you're a helpful assistant, what is the capital of France? And it's going to predict the next word. What it's actually seeing, the AI model is seeing this. Start, it's a system, and it's got you are a helpful assistant, end, I start with a user, what is the capital of France, end, I start, assistant, now what's the next word? So even the idea of system and user is still just another token in the model. A lot of people don't seem to haven't realized this. It's just more tokens in this model trying to predict the next one. And of course, in the model, these are just numbers. So it's just a set of numbers, and what's the next number that goes? Very weird. Now, where have we seen this before? This guy, John Sinclair, said back in 2004, actually way before 2004, trust the text. Just look at the text, see what that's telling you. Don't impart on it these artificial labels. said this: as long as we rely on tags, we are forcing the attention, which is kind of ironic. He used the word attention before attention was all you needed. And the resources on pre-corpus models of language, old-fashioned models of language. Tagged corpora will not meet the needs of the information society. That's what he said way back, and language models don't use tags at all. Okay, so if you look at what an LLM is looking at, well, we have that aspect, but they also learn through co-occurrence, which I've just mentioned earlier a little bit. So you have this model, and they're trying to learn what's the next word, but their context is really huge, but not deep. It's like 8,192 tokens back. It's not like a colloquial model with 5 words to the left and right. This is only looking back, and it's thousands of words, millions now. And it uses that to predict the next word. It's got these embeddings. So we've talked about multidimensional analysis, and we have these 6 dimensions, Bible's 6 dimensions. This has got 2,048. We have no idea what they represent, but it can model 2,048 dimensions in some way. And then you've got this attention, like looking at context, and it's got 32 heads of this, which is a bit hard to explain, and 60 times 16 blocks. So we're looking at these relationships in 32 different ways times 16. So that means we can kind of account for, attend to collocation, colligation, maybe semantic preference, semantic prosody, word type, role, register, genre, all these things. We don't know what it's doing, but it's got the potential, maybe you could say, to do that. And, okay, so we have that co-occurrence model, and this relates back to, in our field, first said way back in 1957, you shall know a word by the company it keeps. That's exactly what that is doing, knowing how these co-occur. But I want to be focusing on John Sinclair. We're in Birmingham, and John Sinclair talked about a thespian perspective on language. This is way before LLMs came out. He said this: there is no familiar, in the thespian perspective of language, there is no familiar set of properties permanently attached to each word. There's no discernible starting point for each word. There's no preconceptions. There's no prerequisites. Only a format for how the lexicon entry will be built up through examining the usage of a word. It's like the framework, like attention. But he didn't know. He wasn't using that term. He also talked about the empty lexicon. A word becomes associated with a meaning through its repeated occurrences in similar contexts. Really kind of similar. I was reading his book. I've got it right here. This one. Trust the text. And it's like reading like LLM descriptions in some way. Sometimes. Sometimes it's different. But he says this: one way of describing collocation is to say that the choice of one word conditions the choice of the next, and then the next, and the next again. That's exactly what we're talking about when we're predicting the next word. And this is, again, said years ago. Kind of interesting. So that's the building part of it. But that's just now the framework. We've got the framework now, and how it co-occurs, and we measure these differences and so on. But then we actually have to build the model. Or train the model is probably the better way to say this. So we have this training on data. So we need to give it some data. A corpus. We need to give it some data and learn what the collocations are. Okay? LLMs require big data, as you probably have heard. So Llama 3.2, which I'm using as an example today, uses 9 trillion tokens. Yeah, I put the numbers here because it's kind of easy to forget what 9 trillion actually looks like. It's a big number. So these models need to constantly revise the model so that these co-occurrences stabilize to the point where they're kind of like perfectly optimized for the entire corpus of 9 trillion words. So big data is key. Okay, and what did he say about big data? John Sinclair said, there's no virtue in being small. Small is not beautiful. It is simply a limitation. The main virtue of being large in a corpus is that the underlying regularities have a better chance of showing through the superficial variations. Big is important. Yeah. Okay, so that's part 2. Really quick, part 2. It's just like you build the model and then just shove in all this data, let it work it all out. But that's not the end, because we have stage 3. And this is a very important part where we tune the model to actually do useful things. Okay? And this is often tuned with something called reinforcement learning with human feedback. Let me explain why we even need this. And this is a very often misunderstood or not known phenomenon with large language models. When we have that level, when we're at stage 2, it's learned all the co-occurrences, but it's not going to be able to speak to us. It's just knowing like the next word, probable next word. So at stage 3, we try and tune that. So I've got this you can go to this website, Hyperbolic's website, and actually show this. If you type in like the cat sat on the, what's the next word in a base model without any tuning at all, it does something like this. The cat sat on the mat, I was at the movies, the movie was about a cat that sat on the mat, the cat sat on the mat, the cat was on the mat, the cat, whoa, it's gibberish. Gibberish. And more interesting, but for me, an interesting thing is like, what about 1 + 2 equals? What's it going to predict as the next word or next token? Now, it's not got any mathematics in here. It's just co-occurrence. So what do you think it's going to do? It's going to find some example in the training data where 1 + 2 was there and give the next most probable word, and it does this. 1 + 2 = 3, 2 + 3 = 5, 3 + 5 = 8, A + B = C. Well, it's just like from a textbook. It's got no idea what mathematics is. It's not understanding mathematics. It's just pulling out something from the training data that looks like 1 + 2 is, and then following on. So we need to tune it. So this fine-tuning is an essential component. In post-training, we engage in this synthetic data generation, so forget authentic now, that goes through carefully data processing and filtering to ensure this high quality of the model. We carefully blend the data to optimize for high quality across multiple capabilities like summation, rewriting, translation, instructions, chatbots, reasoning, tool use. How do you do that? Well, it's just like this. You give the model, you are a helpful assistant, what is the capital of France? And you say, you should generate Paris as the answer, not some gibberish like the cat or something. Don't repeat. Come out with that one. And if it doesn't, you say, relearn. Keep learning until you get that as the right answer. And you do that thousands of times. Thousands of different examples. I actually have an example. This is from Anthropic. It's not what Llama 3.2 used, but this is a real example of what we use for training, fine-tuning models. So what kind of noises did dinosaurs make? Humans and dinosaurs didn't live at the same time, so it's really hard to say. Now, this is not what the AI is generating. We are telling the AI to say that as the answer. We're saying, you should generate that as your answer. And it looks at that and it learns that, and then suddenly it's magical. It can do it not only, just going back, it can not only do that with Paris, then it starts doing it with the UK and Germany and Japan and China and every other country. Once it's got the concept of like question-answer, and we're talking about countries, then it can start doing this with every country. And it starts becoming kind of magical in that way. But you get the idea, like what's happening here. Okay. So if we've got a tuned model, or a post-trained model, like Llama 3.2 Instruct, which has been trained to answer questions, now it can do this. Yeah, the cat sat on the mat, and it stops. It works great. Okay. So let's think about the theory behind that from our perspective. So LLMs require this guidance, they require motivation, they require goals, and we give them the goals. You answer with a city. Don't say something else. Do that. Do that. You train it. So in our field, we actually have some linguistics theories that kind of support that way of thinking about language. Well, this is a bit liberal now, but universal grammar, Chomsky, he's right, kind of. Because he said humans are born with an innate linguistic framework shared across all languages. And those AI models are multilingual. They work, the same box works with any language. It is a kind of universal framework. I know it's not quite like what Chomsky's saying, but I'm trying. We've got Skinner saying language learning is a process of habit formation through reinforcement and repetition. And that's exactly what they're doing when they're learning these co-occurrences. Social cultural theory, Vygotsky says, interaction with more knowledgeable individuals and participation in cultural practices are essential for language development. And we have that with the model. When it gives you gibberish and you say, no, you should be doing this, you're the informant telling it how it's supposed to be learning language. I'm pushing the analogies a little. But you get the idea, I hope, that it's not completely different. So kind of, yeah. What about cognitive psycholinguistics? Language acquisition results from the gradual strengthening of connections between words and meanings through exposure and experience. I would say that's pretty close to what they're doing. Social linguistics, social factors such as class, gender, ethnicity influence language variation and change. We find that in the data. Yeah, if we give different, it's a bit of a touchy issue, but they will change depending on what words are coming in. Okay, forensic linguistics. Each individual has a unique linguistic profile encompassing vocabulary, grammar, pronunciation, writing. So it's learning the differences between text. It's learning all these variation across all kinds of dimensions. Gender, race, whatever. Okay, as it comes in. And then last one, that's kind of yes. Last slide from this. Pragmatics, language use and meaning is shaped by context, speaker intentions, shared knowledge, social norms. Well, it's definitely shaped by context. We had this at the conference, but it's also seeing that context and it's shaping its learning based on that. Conversational analysis is systematically organized where participants are adhering to implicit rules that govern turn-taking, sequencing, and repair mechanisms. It's a little bit more difficult to put that in. But I hope you see it's not completely different. And the last one I think is really, really related. Words and phrases acquire different interpretations based on the situational and cultural context in which they are used. Now, AI models don't see the context outside of the window, that window. They don't see the world. They're not embodied. They don't go around and see what culture they're in. But they can kind of get some hint from the input. And they do learn based on that. But of course, there's a lot of work to be done. And I've been writing notes, like what Gavin was saying, just like, models don't do that. Maybe if we gave that to the model, maybe it would actually learn more and be better. Okay, so kind of yes, but I know I'm pushing it. So second hot take then. So large language models align well with many existing theories of language acquisition and use. And future developments in LLMs can be informed by our research. The more we know about how language works, we could tell the LLMs developers what's happening with real language, and maybe they would start getting better because of it. Like if they went to Gavin's talk, those developers, they would realize we need to get embodiment into this system pretty quick because we can't model all these factors that are really important. If we're, again, with Lizzie's talk, if you want to develop conversation, like if you want to have a really good conversation with somebody, you need a whole lot more factors than just the context window before it. Empathy, how is empathy in there? What's joking? How is joking represented in there? Okay, so as corpus linguists, should we incorporate LLM views of language in our research? Should we be forgetting tagging? Should we be ignoring, not ignoring dimensions, but increasing the number of dimensions, for example? Should we be informed by these models? And as corpus linguists, how can our views of language impact AI research? Are we going out to the computer science people and telling them what we know about language? Because they would be interested, almost certainly. Okay, so there is one weird thing about this. This is the standard way of fine-tuning the model. We tell it what to do. But there is a new way. Stage 4 is called reinforcement learning, true reinforcement learning, where there's no human at all. And this gets scary. Because we can have automated reinforcement where you just give a goal and the model tries to find a solution to it. And that gets really weird. I tried to think of a clear example of this, but it would be like learning how to use a calculator for math. It doesn't know how to get the right, 1 + 2 = 3. It might get the wrong number, right? So the only way to get the right number is to use a calculator. Like go off, use a calculator, come back with the answer for that. Type it in and get the answer back. You don't tell it to do that, but you just give it the option to use a calculator. And then you let it run and keep getting the wrong answers until one day it suddenly realizes it could use a calculator, and it starts using it, gets the right answer, and it learns to use that more and more. It's kind of bizarre. It's like a human a little bit. But once you have that ability, they become superhuman. If you think, why? They can start doing things that we just can't think about. They can go way beyond our abilities. And we already see a hint of that with this thing called DeepSeek R1, the first reasoning model, true reasoning model. And they say in this model, DeepSeek R10, a model trained via large-scale reinforcement learning without supervised fine-tuning, it's none of us, as a preliminary step, demonstrates remarkable reasoning capability. It just thinks really well. Can solve really complicated problems, PhD-level problems and things like that. So that's the next stage that everybody's working on. It's kind of worrying in some sense. Okay, last part. Oh, time's going good. Okay, how can we advance this corpus linguistics research, and also maybe how can we advance LLM research as a group, as a community ourselves? Okay, so what we know is that LLMs excel in qualitative tasks. Context-dependent, nuanced, subjective, creative tasks. They're really good at that. They make hallucinations sometimes, but as you saw when I was talking to the ChatGPT model, it was pretty good until I asked it about frequencies, and then it starts getting fuzzy. And you probably thought, oh, that's not so good. At the end, it started getting weak, right? Didn't know the frequencies. It starts giving some general ideas. So it excels at qualitative tasks, but it's less reliable at quantitative tasks. Numerical things, measurable things, objective things, like who developed Anconk. It's going to like, oh, Mark Davis? John Sinclair? When it comes to like picking the exact things, it starts getting weak. But like general fuzzy like that, it's pretty good. Okay. But every day they're getting better at these quantitative tasks. And this is a quick example. What is this huge number plus this huge number? You can't see that so well. But it gives you this other huge number, and if you put it into a real calculator, it's correct. How the hell did it do that? Because it used a calculator. It went off and thought, that's a sequence of tokens that I cannot predict the next word for. But I can use a calculator, type it into a calculator, and get the answer, and then give that back. So it got it right. It can do it perfectly now. It's kind of scary. That's reinforcement learning to it as an example. In a corpus of electrical engineering research papers, what is the most frequent word? Well, the most frequent word in a corpus of electrical engineering research papers is typically the. Just like in most English language corpora. So the fluency is amazing, but the quantitative stuff is a bit weak. Okay, however, if you're asking about the most frequent technical or domain-specific words, that depends on the specific subfield, blah, blah, blah. That said, across general electrical engineering literature, some of the most common technical words are, and then we get gibberish, potentially. Because it's trying to do something that it's not good at, picking out these actual frequencies. It can't count, basically. These models can't count unless they use a tool, like a corpus tool, to count, and then come back. Okay, so that's the LLMs. They're great at subjective, qualitative stuff, but they're really bad at counting. What about us? Corpus methods excel in quantitative tasks. We do lots of counting. Coming back to this morning's plenary talk, Charlotte and Anna was talking about counting and all the different ways that we count and why it's important. We're great at counting, and they're terrible at counting. Okay, so corpus methods excel in quantitative tasks, but they're hopeless at qualitative, right? The methods, the tools are hopeless at qualitative stuff. They tell us nothing apart from the numbers. And then they rely on us, humans, for the qualitative interpretation. That contains dependency, the nuanced, subjective, creative task. That's what we do with those numbers. How are we using those numbers? That's for us to decide. So we have this interesting interplay, I feel. We have these LLMs that are great at subjective, fuzzy models of language, and then our counting. So can we integrate the two? Can we integrate AI with traditional corpus methods in our research, in our teaching, in our learning if you're a student? I think the answer is yes. And we have seen it already. I'm talking to a group that already knows a lot of this because we see so many great research presentations at this conference already that look at using AI in research and seeing how it differs from humans and so on. Just now we had a new way to measure keenness with AI approaches with an LLM and so on. So there's all kinds of interesting work being done. Okay, so my idea is to try and facilitate this for the people who might not be able to go off and get a large language model and run it in the labs. Okay, so I wanted to try and develop a platform for this AI corpus. Experimentation is probably the best way to put it. So it's for us to try out things and experiment and see what these models do and why they learn why they make mistakes or find what is useful for the classroom or what's not useful for the classroom and so on. So we have this problem, though. So we have all these AI tools, chatbots, image generation tools, audio processing, and we have our traditional methods. Can we bring them together? So I've visualized it here on the right. So we have all these models. Can we bring those together with something like Ancon or a traditional corpus tool? And that's what I've been working on. Just before I introduce that tool, we have to understand the different types of models we have in AI. So we have cloud-based models like this, and I'll just show you both, and then local models, and they're quite different. So cloud-based models are things that probably we've all seen and maybe used. ChatGPT, Claude, Grok, Copilot, Gemini. So they are proprietary, public, commercial, black boxes in the sky. Okay, but they have amazing performance. They're fast, accurate, more reliable. They don't hallucinate as much. These local models, they're open source, open weight, private, free, really good, but then they have worse performance. They're slow, generally slow, and they require good hardware to work faster. The better hardware, the faster they go. And on Windows, this Windows machine, they're slow. On my Mac, they're fast. Apple Silicon is amazingly fast. This hardware is slow. But if you have a big desktop, that would be fast. And they're less reliable. They hallucinate like crazy. As I showed you earlier, those examples of Ancon being developed by John Sinclair, that was a local model. If you put it in OpenAI, it's perfect. Okay, so I've got these two worlds, and I want to try and implement them both into Ancon's integration. So this is now Ancon 4.4, and it's available right now to download. It's on my website right now. In fact, I remembered to show you. I was thinking I was going to forget to show you, but it's right here. If you go to Ancon's webpage, you can go down, and you can see beta release of version 4.4. Try it out later. See what you think. So what this is, it's giving you access to all these different ways of using AI. So the first way is simply to go to OpenAI through its API key, and you get the best models, still probably the best models in the world. You can chat with them and use them. But I also have a bridge to LLM Studio, which is a framework to manage local AI. You can easily download models and change the weights and temperature and play around with it. Very nice. But it is a bit complicated. I was thinking how I would introduce that to a student in the class, and it's like, wow, that would take a week or two just to explain LLM Studio. So I also thought of another approach which would be useful, and it's this llama file, which is a language model in a box, like a corpus in a box. It's just a single file. Sounds crazy that you could have a single file, which is an AI, but we have. It's just a single file language model. In fact, you can put these, going back here, you can put, not these, but you can put many of these models into that box. Thousands, millions of them. Well, thousands. Several tens of thousands of these models. You can wrap them up and use them locally. So I've got this Corpus AI integration, which is a bridge from standard Corpus tools to Chat AI, and that's my interface here, so that we can get our local results and get them and start talking with AI with them for experiments, insights, explanations, expansions. We can bridge from AI to our corpus tools and go the other way. And if we want to query our local corpus, and we don't know regular expressions, for example, we can ask the AI to generate the regular expression for us and then prompt it like normal. Just do a normal search. If you get that idea? You can use AI to help you just do a normal search. And hopefully I've got time. It's 50 minutes, so I have to be careful with my time. But this is the kind of interface that I'm talking about. But let's do it live just to see what a disaster we can have at the end of the talk. I hope it's not. OK, so this is real. OK, this is live right now, version 4.4. So I'll just do something which is normal. OK, so we go to the Corpus Manager, and we'll load in a corpus and get some results. OK, so we go to the Corpus Manager. It looks different to what you've seen in the past, I know. But we go to the AMI06 learned, and we just say, I want that to be a target corpus, and say OK. So now we have that, and we could do something like study and see what's in there, and we get the results. We've all seen that before. I'm going to limit the results a little bit just for this demo, say 50. OK. Now, we can then go to something like Chat AI and talk about it. Ask the AI about our results that we just got for insights and so on. OK, so just a minute. Well, which model do we want to use? Do you want to OpenAI's model, or do you want to use LM Studio, or do you want to use a language model in a box? Well, let's use it in a box. OK, so we would go here to the AI Manager. And here we have all our models. And I say, I want to use this 3.2, Llama 3.2, which I've been talking about today. And we just say, do that. It's going to just start, hopefully. Yeah, OK. It's ready. And now we can use it. OK. Now we have AI running, local. Nothing to do with OpenAI, no cloud, nothing. OK. And now, in this prompt, we can start talking. So I can say, like, hi. Did you notice a little delay? That's because it's local. It's not as fast as normal. Hello, how can I help you today? And say, OK, what are the most frequent words in English? I am aware of the time, but you know I'm nearly finished. OK? So the local model is looking at that according to various sources, including Oxford English Corpora, and then we have this. OK? It's not good at that. Don't do that. Because it can't count. We shouldn't, if you want to know the most frequent words in English, use the word list tool and do that, you know? That's what you want. But then you want to ask it about it. Maybe you want to ask the model about it. Now, originally my idea was at this point to click on source, like the quick concordance results I just generated, and ask it about this. And on my Mac, that would have been fine, but on my PC, it's too slow for this demo. So unfortunately, I can't just do that because it'll take about a minute to come back because it's local and this machine's slow. So let's just let's change the setting. So I'm using, where's my AI settings? I'm using here Ankong's AI Manager. Let's go to OpenAI because that is super fast. And now I can say, OK, in my quick results, how is study used? Very just normal, right? So we have the results in our quick concordance. We see study of and so on. I'm just going to ask it about it. Now, it's saying, you have to pay. OK, I know. Because we're using OpenAI now. But now, I'm thinking from a student's perspective. They may be a second language speaker who doesn't know what all those concordance lines mean. And as a teacher, you can help them through that. But if they want to do it on their own, data-driven learning at home, they may ask that question to the AI, and the AI can then, I'll just turn that off, generate the results. OK. And it's just going to keep going. And it's fast. And this result is going to be pretty good. Now, it will hallucinate a little bit, maybe, but it's got its raw data from the corpus. So it's got that grounding, at least, and it's looking at that before it's giving any answers back. So I think I'm not trying to use this demo to say you should be using AI in the classroom with your students, but it's really more like, as corpus linguists, we should be interested in what it's kind of generating. Why does it make mistakes? How could it be used usefully in the classroom? If you're a teacher, like, how would you use that? And students are using AI anyway. So, like, how could we learn about it and maybe use it in the classroom and get some insights and so on? As a researcher, as a teacher, as a learner, how does this all work? And that's the kind of idea for this. So it's not an idea of you should be using AI in the classroom and just forget teaching. It's a matter of this is a bridge to these ideas, and you might want to play with them and see what they're like. Okay, so final thoughts. 55 minutes, sorry. Large language models are a truly astonishing new technology, I think. It's magical. In a positive way, I think it's a magical, astonishing new technology. They align well with, and there it is. I haven't said it the whole talk. I've traditionally been a corpus-based linguist, if you know my work. This is the first time I think I've ever had that on the screen. They align well with corpus-driven theories of language, and they're far from perfect and can be greatly improved. Our methods are clear, transparent, reliable. They give good insights on language usage. They can possibly benefit from the engineering sophistication of LLMs. Our methods can benefit from them, maybe, and can possibly lead to new insights in LLM design and applications too. So there's both ways, I think. AI integration with Corpus Linguistics is a possible next step. I've hedged everything in the advancement of both fields, I feel. I'm going to finish with one last quote. So, John Sinclair said this: I believe that we should first consider how likely we ever are to reach a position of being able to rely on the machines for even simple tasks involving the understanding of open text. Now, open text means real, like just normal text in the wild. Okay. How can we ever do that? He was saying back in those days. It was a pipe dream to be able to do it. Okay. If it appears to be a tractable problem, if we can do it, if we think you can do it, then I think the whole corpus linguistics community should go straight for solving this problem in a series of blue sky attacks, because the rewards are so great if we can achieve that goal. And I'll finish there. Thank you.